So linear equations. So this section we're actually going to learn how to solve for an actual differential equation. The first part we're going to do is how do we actually write in a standard form. So the way we write in standard form is, well, we're first going to be given to usually in this kind of situation. And standard form basically means I want the derivative to be by itself, or just a 1 in front of this. So the first thing we do is just divide the entire thing by a sub x, ace1 of x. So we end up getting something like this. Okay. Now again, this looks pretty bad to look at, and itself, ugh, horribleness do. Let's see if I can focus this real quick. Okay, there we go. All right, so first thing we do is divide this both sides, and again, we get fractions. But like everything else, we don't like fractions to begin with, so what we do is just rewrite it in a different format. So we just let this be p of x and q of x. But really, in a little bit nicer format, this is what we're really looking at. Right, or just y prime by itself. There's some constant or a of x in front. That's what we call p of x, and then b is b of x, or just constant there. Okay, that's pretty much what we're looking for, is make it look like this. Okay, so unfortunately, the first thing we have to do is something called a integration factor, and you'll see that much more later on. But for now, we barely introduce what this represents. Okay, an integrating factor is a function we'll call u of x, such that when I multiply the entire thing by u of x, so meaning all of this or all of that, this middle part is u prime. It ends up being u prime of x. So in other words, again, if I multiply everything by u of x, this part right here ends up being the derivative of just u prime. Okay? So somehow that works. Okay? Now, wondering why would you do such a thing? Okay? Well, there's a reason to all this kind of method, right? In madness itself. So again, we'll just start from here. So all we have to do is now solve for u of x, and that gives us this part here. And if we just take the e to the eventually, we get this. Now this is what we care about, because this is how we actually find an integrating factor. So this is going to be what we're actually looking for in this case, right? Now again, why do we care about multiplying by u of x to begin with, when we don't want a number in front of here? We want just a 1 in front of it. Okay. Now the best part is, if by doing this process we actually simplify things a lot further. Okay. Or in other words, instead of having everything in terms of just y prime plus some constant y, we engulf this all into one single equation. Because if I look at the left side, which is all of this here, and this is actually, and if this is just u prime itself, this is actually an implicit differentiation. This is taking the derivative with respect to x in both cases, or just that with the y in front, right? This is a product rule, so implicit differentiation, take the derivative of this gives me u prime, plus taking the derivative of this is just this by dy dx. It's an implicit differentiation. So really, we just simplified one side. That's pretty much the whole reason why we're doing this long process, is make this much easier to actually simplify and actually do. Okay. And that's what we do. So in other words, the left side now becomes this, and the right side still is q of x times the u of x itself. But this is much easier to deal with, because now we just take the integral, of all of this, just divide this all over, and we get y of x after some much simplification itself. Okay. So this is called our general solution for any linear differential equation of this format. Okay. All right, so that's a lot of talking, a lot of figuring out what's going on, again, a lot of math. So in layman's terms, what we have to do is, first thing I do is make sure it's in that form. Second thing we got to do is find the integrating factor. And then finally, the third form is actually solving for it, meaning finding the general solution of a linear differential equation. Okay. And that's what we do here. Okay. All right, so steps into solve it, just like I highlighted. First thing you want to do is write it into its standard form, or in other words, dy dx plus p of xy is equal to q of x. Find the integrating factor. So that means u of x is equal to the integral, or e raised to the integral of p of x itself, which is kind of nice. So that looks a little funny, but most of the time it's going to be kind of nice. Multiply both sides by u of x, so we basically get u of x times q of x is equal to this u prime, or just the partial derivative of that. And then finally, we just integrate and just solve for y, or we just use the general form. Okay. So let's try this out and see how this would work. Okay. All right, so find the general solution to this. So step one, we have to put it into the form we want it to. So in other words, we have to multiply everything by x, because I don't want that there. So I'm just going to make it easy to put just y prime. So minus multiply by x, we get 2 over xy, and gets x squared cosine of x. Okay, so now step one is done. Got it to that form. And I'm just going to write down what we have because I know I need p of x and q of x everywhere I need it to. So in this case, p of x is going to equal to negative 2 over x. And q of x is cosine squared x squared. Okay. All right, so that's going to help us with step 2, because step 2 we want to find u of x, so our integrating factor. And our integrating factor is e raised to the integral of just this. So if I put the negative out here, it's 1 over x dx. And the integral of 1 over x is natural log. So that gives us that. And if I bring this to the top, because I really don't like this e stuff, I now get this. And logs and e's cancel, so eventually u of x is equal to x to the negative 2 power. All right, so now done with step 2. Now we go on to step 3. Okay, so step 3 is pretty much multiplying by u of x. So we multiply u of x by both sides of the equation, or just by q of x. So that's this part here. So step 3. So u of x times q of x is equal to, well, x to the negative 2 times x squared cosine x. And that's even nicer because the x squareds cancel, and we just get simply cosine x. And now we can finally go to step 4. In step 4, we wanted our general equation. And according to our general equation, it's going to be y of x is equal to the integral, well, oh, sorry, put this in, 1 over u of x, and just write it for you guys, times the integral of this multiplication, u of x times q of x, dx plus c, like that. And now we just plug in what we know. Right, so this is 1 over this, so 1 over e x to the negative 2 power times the integral of just cosine, which is really nice, dx plus c. Well, integral of cosine is sine. This ends up being x to the positive 2 now, plus c. And then finally distributing the x squared gives us our general equation. And then we're done. So about 4 steps, nothing too crazy. The integration wasn't too bad, right? Now, based off this now, we can actually do a couple more problems, especially for one from chemistry. Is a rock contains 2 radioactive isotopes, Ra1 and Ra2. They both belong to the same radioactive series, meaning RA1 decays to RA2, so this one goes to this one, then decays into stable atoms. Assume that the rate at which RA1 decays into RA2 is, and they give us this equation, because the rate of decay is RA2 is proportional to the mass of RA2 present, the rate of change is this part. Alright, so basically after all of this horribleness, they finally give us an equation. And this is a differential equation. Alright, sounds good. Okay, perfect. Alright, so this is in terms of t instead of x, but it's the same process. Question is, find the mass t of y of t of RA2 for t be greater or equal to 0 if k equals 2 and initially we have y of 0 equals 40 kilograms. Okay, so that's our initial condition, right? So we have a linear differential equation and we're going to solve for its initial condition. So we have initial value problem. Okay. So let's bring everything, because now we have to do one extra step, is to find our c value here because we have an initial condition. We're also told that k is equal to 2, so that's what we're going to plug in right here. So after all of this portion, we basically get y prime is equal to 50e to the negative 10t minus 2y. Okay. So again, first thing we're going to do is convert it to its proper form, meaning bring it over to this side. So we have y prime minus, positive now, 2y is equal to 50e to the negative 10 t. Alright, so step 1 is done. So now we go to step 2. We have to find our integrating factor. So that's e raised to the integral of p of x, and p of x in this case is just going to be 2, and q of x is the 50e to the negative 10, or t in this case. So this is nice, just integral of just 2 dt this time. Integral of just 2 is just 2t, so this ends up being e to the 2t. Alright, so now we go to step 3. So step 3, I multiply this by q of x. So this is going to be a little bit more careful of. Okay. So remember when we multiply exponents, we're technically adding. So 2t minus 10t gives you negative 8t. So that's the result of that. Okay, so now we're at this point. You go to step 4. You plug everything we have in. So y of t is equal to 1 over our integrating factor. So that. Or just e to the negative 2t times the integral of this plus c. Right? So this is just a quick u sub, if you guys are wondering. So let u equal negative 8t, du is negative 8 dt, so we just divide that over, and we just get e to the t, which is just itself. So this stays here. So this integral ends up being negative 50 over 8 because of the negative, e to the negative 8t plus c. Okay. All right. So distribute this, all this fun stuff. And notice we still end up getting e to the negative 10t. Gives us that. Now, if we wanted the general, it would have been done, but we have an initial condition here. So when t is equal to 0, our y value is equal to 40. So setting all that process here gives me 40 is equal to, well, t equals 0. That's just going to be 1, so it'll be negative 50 over 8. Plus, if this is all 0, this is 1, so we just get that. So adding this over, we found out what c is. So in fraction format, we get about 185 over 4 after we simplify. So therefore, our equation, not our general one, our actual equation with respect to this partials, is equal to, I guess I can simplify this, but nothing too big deal of. Positive, yeah. And there we go. Okay. So let's try one more. So find the general solution of a linear equation. Again, so if you don't like this, just rewrite it. I'll leave it like that for sake. Okay. Now this is a bit deceiving because again, I want it in all the y's at one side, right? So first thing I have to do is actually subtract this over. I'm going to put this in parentheses as well, just so you can see. Because now we have our situation. So we have p of x is equal to negative 1 over x, and we have q of x is the entire thing of 2x plus 1. Okay, so now we go to step 2. Find an integrating factor. Bring this on the outside. Which ends up being e to the negative ln. And if you notice, kind of a bit of a pattern with ln's and e's. We just get x to the negative 1 power. All right, so now we go to step 3. Multiply this by q of x. So if I distribute this, this is kind of nice. This ends up being just a 2, and this is now I'll write it as 1 over x, since I'm going to take integral right now. So that's that part. And then finally, our general solution, be 1 over this process times integral of that plus c. Okay, so this nicely ends up just going upwards because it's a negative becomes a positive. This integral becomes 2x plus ln of x plus c. And then I just distribute the x. And there we go. We got what we wanted.